Hey, இறங்கி கதவு தர நான் சைடு டயர் இருக்கிறேன்.
Is the screen visible to all? Good morning to one and all. Is the screen visible? And am I audible to all? Am I audible to all?
Yes, sir.
Okay. Is screen visible? Visibility of screen?
Yes, sir.
Okay. So thank you, Naresh. So we'll start today's session on the solutions to problems in unit number 2, which is information channel. So in last class we had solved some 9 problems. So the left out problem we are going to see today. So far whatever we had seen in the information channels questions and solutions is solving using a binary channel, a binary symmetric channel, binary non-symmetric channel. So we had seen this. So in this specific problem we are going to concentrate on a ternary channel. Okay, ternary channels. If we say it as a binary symmetric or a binary non-symmetric channel, the channel will have two sources, x1 x2, and two outputs, y1 y2, is the case till now we had seen in the previous classes. Now in this problem we are going to see ternary channel where m is equal to 3. So if m is equal to 3, we call it as ternary channel. Okay, so for this problem the transition matrix is given as 1 0 0 0. I'll highlight it. 1 0 0 0 p 1 minus p 0 1 minus p and p. So we all know that in a ternary channel matrix the first represents is p of y1 over x1. Second one is, because all the rows are inputs, all the rows are inputs, so x1 x2 x3, and all the columns are outputs, so y1 y2 y3. So the transition matrix can be given as p of y1 over x1, p of y2 over x1, p of y3 over x1. And in the second, p of y1 over x2, p of y2 over x2, p of y3 over x2.
போஸ்ட்டுக்கா நீ வண்டியா போறேன்
P of y1 over x3, P of y2 over x3, P of y3 over x3.
துணியில ஏத்தாங்க காய போட்டு வெயில் நல்லா இருக்கு.
சாப்பிட்டியா சாப்பிட்டியா
So the equivalent of these values are 1, 0, 0, 0 p, 1 minus p, 0, 1 minus p, p. Equivalently with the channel transition matrix. So for this we need to first draw the ternary channel diagram. Ternary channel diagram. So how to draw this? I'll tell you. So for this problem we have to determine the source entropy, h of x, mutual information I of x is to y, and also determine the capacity of the channel. So these things, three things we have to determine. Assuming that the source probabilities is given as p of x1 is equal to p and p of x2 is equal to p of x3. P of x2 is equal to p of x3. So these are the things being given. Okay. Now take 3 points. 3 input points.
எதுலயே மாதிரி வேற கெமிக்கல் மாதிரி போட்டு
I'll show you how to draw. Just a minute. You're having 3 points. I write it as x1, x2, and x3. So these are the 3 input points. And we have 3 output points. Take a brush. So assume these as 3 points with outputs y1, y2, and y3. So 3 inputs, 3 outputs. So now see the question. Let me navigate to the question. Question is, we are assuming p of x1 is equal to p of x2 is equal to p of x3. Okay. So how to draw this? So from the given question, x1 and y1 is 1. P of, in the place of the matrix channel, you see x1 over y1 over x1 is 1. Okay. So then in the place of y2 over x1, so let me draw it here. y2 over x1 is 0. It is not present. And y3 over x1, this is also 0. Stage by stage I am drawing, so keep in mind. So this is for x1. So next I'll draw it for x2. So for x2, y1 over x2, which I'm highlighting in blue color, is 0. And y2 over x2 is p. This is all from your channel matrix. Again in blue color it is p. And y3 over x2, y3 from x2 to y3, x2 to y3, it is 1 minus p, 1 minus p. So x2 input with all the y1, y2, y3 outputs is drawn in blue color. Red color is for x1, blue color is for x2. Now let us draw for x3. Okay, so p of y1 over x3, I'm drawing in green color, which is 0. Then p of y2 over x3, y2 over x3 in green is 1 minus p. And p of y3 over x3 is p. So this is how to start with the diagram. This is how do we start. Okay, let me save this. This is how to draw the channel diagram for the ternary channel. Okay. So now what we are going to do is that we are going to erase, we are going to eliminate wherever we have got the channel transition as 0. So what are the cases that you have got channel transition as 0? One is x1 y2, another one x1 y2, another one x1 y3, x2 y1, x3 y1. All these 4 transitions can be erased. So if we erase these transitions, we will get this diagram. We will get this ternary channel diagram. So any doubts in drawing this ternary channel diagram? Channel diagram drawing. Any doubts for anybody? Okay. Since there are no doubts, I'll go for the next. After drawing the channel diagram, Let me check in the chat box for questions. Okay, no questions. So I'll proceed on further. Now, after drawing the channel diagram, we need to determine entropy. Entropy h of x. So for determining this, we should be familiar with the given source probabilities. The given source probabilities are P of x1 is equal to P. So always our probability is that P of x1 plus P of x2 plus P of x3 is always equal to 1. And since P of x2 and x3 are same, we can substitute here it also. Is equal to 1. And since these take it on that side, we get P of x2 is equal to 1 minus P divided by this 2 there, and P of x3 is also 1 minus P divided by 2. You will get it as 3 different values. P of x1, P of x2, we get P of x1 as P of x2 as 1 minus P by 2, P of x3 as 1 minus P by 2. Now, we are going to determine the entropy, source entropy. We know the formula for source entropy. H of x is equal to summation k is equal to 1 to m, since we have 3 symbols. So take that. Substitute P of x1, P of x2, P of x3. Simplify it. You will be getting this equation 1.12.41. So try to simplify that and see whether you're getting this equation. Next is to find entropy. So conditional entropy h of x over. Are you familiar with this formula? We know that h of x over y is given as summation I is equal to 1 to n, summation j is equal to 1 to m, p of xi yj log to the base 2, 1 divided by probability of xi over yj. So this is the formula. We have done problems on this also. So similarly, find it for x1 y1, x2 y2, x1 y3, x2 y1, x2 y2, x2 y3, x3 y1. Simplify the terms by substituting equivalent values. P of y1 over x1 is there as 1 into P of x1 is P. We get P. P of y2 over x1 into P of x1 is 0 into P is equal to 0. And similarly, you have 0 into P is equal to 0. And for the next y1 over x2 into P of x2 is 0 into 1 minus P by 2, which is equal to 0. You can refer P of x1, P of x2, P of x3 here, and P of y1 over x1 all in this channel transition matrix. So simplify, we get values. Let me down this. We'll be getting these values for p of x3, y2, p of x3, y3 as this on simplification. So take all this, substitute in this equation, determining p of x1, p of x2, p of x3, y1 over x1, y2 over x2, y3 over x1, y1 x2, y2 x2, y3 x2, y1 x3, y2 x3, y3 x3. So substitute equivalent values. Then substitute p of x1, p of x, simplify them by row versus column. Multiply this row and row, this first row, first column, and first row, second column, this row and this column. You'll get these values. So p of y1 is obtained, p of y2, p of y3. So these are your simplifications. You need to use this simplification methods that you all are familiar by using matrices. Now we need to find for I of x is to y. Next is to find p of xi, yj. So find p of x1 over y1 as this, x1 over y2, x1 over y3, x2 over y1 using this formulas. So we'll be getting 1, 0, 0, 0. Just a minute, it is not moving. I will check it out. Yeah. x2 over y2, x2 over y3, x3 over y1, x3 over y2, x3 over y3. You'll get all these things. You can simplify them easily. So now substitute all these things in h of x over y, which is our conditional entropy. So substitute in the conditional entropy. P of x1 y1 log to the base 2 1 divided by p of x1 y1 plus p of x1 y2 log to the base 2 1 divided by p of x1 over y2 plus p of x1 y3 log to the base 2 1 divided by p of x1 y3 plus p of x2 y1 log to the base 2 1 divided by p of x2 y1 plus p of x2 y2 log to the base 2 1 divided by p of x2 y2 plus p of x2 y3 log to the base 2 1 divided by p of x2 y3 plus p of x3 y1 log to the base 2 1 divided by p of x3 y1 plus p of x3 y2 log to the base 2 1 divided by p of x3 y2 plus p of x3 y3 log to the base 2 1 divided by p of x3 y3. So from all this, on substituting, we will be getting this equation. P of log to the base 2 1 plus 0 0 0 0 3 zeros plus p of 1 minus p to the p of p into 1 minus p by 2 log to the base 2 1 by p plus 1 by p into 1 minus p by 2 log to the base 2 1 divided by minus p plus 0 plus 1 minus p into 1 minus p by 2 log to the base to 1 divided by 1 minus p plus p 1 minus p by 2 log to the base to 1 by p. Okay, let me move on to the next. On further simplification, we will get this p of 1 minus p log to the base to 1 by p plus 1 minus p into 1 minus p log to the base to 1 divided by 1 minus p. So 1 minus p, take it as common. So remaining will be p of log to the base to 1 by p plus 1 minus p log to the base to 1 by 1 minus p. So this is your h of x by y. Our conditional entropy we had found. So from the question we need to find next is mutual information. Mutual information is I of x is to y is equal to h of x minus h of x over y. So substitute h of x, substitute h of x over y. So h of x we had found, h of x over y. So write this. This is your mutual information. After finding mutual information, we need to find the capacity of the channel. It is our major task in this ternary channel. Well, because mutual information and the conditional entropy were very easier to find, and it was very much easier to determine. So now, still now we haven't determined any channel's capacity. Just we had seen the formula and just we had noted how to solve it in theoretical, but not in a problem. So here is the procedure how to solve or how to determine the capacity of the channel, especially for a harder part of ternary I had taken. So this is what the choice of this problem is for solving. So here I am going to determine the capacity of the channel also. Okay, so there are three different points to be noted for determine the capacity of the channel. One is we need to know the channel condition. So whenever channel condition is known, it is easier to determine that. So for determine the channel condition, we should be familiar with mutual information. Why? Because the capacity of the channel is C, where we have the maximum probability of occurrences of the input sequences over the mutual information. The capacity of the channel is dependent on the mutual information. So this is what is required for the capacity of channel is. Okay. So there are three steps to be followed. First one, differentiate the mutual information with respect to P. Then solve it for information is equal to 0. Channel capacity. Okay, sorry for the interrupt. Determining the channel capacity is obtained from mutual information. For this, we need to have three steps to be followed. One is differentiate with respect to P. Then solve it. The differentiated with respect to P value is equal to 0 for P, and substitute the value of P that we had obtained in this mutual information. We substitute, we'll be getting channel capacity. So for that, take the equation I of x is to y. Take this equation, differentiate with respect to p. Say this p, differentiate, and consider this value, whichever is present, p log to the base to 1 by p plus 1 minus p log to the base to 1 minus p as a small constant value. So I'm denoting this, only this value as beta, that's all, because we don't have a p here. Okay, so beta, just a simple notation beta here. So this is one, so that you can easily simplify or you can easily differentiate. So differentiate this, so you know logarithmic p into p, you'll get this. For this, so at last this is your equation. So differentiation of mutual information I of x over y divided by dp is equal to minus p into d by dp log to the base to p plus log to the base to p of p minus 1 minus p d by dp log to the base to 1 minus p by 2 plus log to the base to 1 minus p by 2 minus into minus 1 minus beta into d by dp 1 minus p. Simplify further. You need to simplify further. Use this step-by-step method, and you will get. Use your anti-log. You will get this value minus log to the base 2p plus log of to the base 2 1 minus p divided by 2 plus beta. Okay, for this we need to equate this value is equal to 0, the differentiated value. This is an important condition for obtaining p. So equate this as 0, so this will be equal to 0. Rearrange in terms of beta, so beta will be equal to log to the base 2 plus log to the base 2 of 1 minus p by 2. So further simplify by your mathematical tool, we will get the value of p. From beta you find p. These are the steps in sequence. Mathematical simplification procedure. So p is equal to 2 power beta divided by 2 power beta plus 2. Next, after finding this value of p, we had found p value, which is this. Simply substitute this p value in mutual information. Mutual information. So mutual information is this, which you had obtained. Simply instead of p, substitute this. Okay. And simplify step by step. You all are more familiar than me in simplification. So minus 2 power beta divided by 2 power beta plus 2 log to the base 2 2 power beta divided by 2 power beta plus 2 minus of 1 minus 2. Instead of p you are substituting 2 power beta divided by 2 power beta plus 2 log to the base 2 1 minus 2 power beta divided by 2 beta plus 2 whole divided by 2 1 minus 1 minus 2 power beta divided by 2 power beta plus 2 into beta. Simplify this. Reduce the terms by using your mathematical tool and see whether you're getting the information as log to the base 2 2 power beta plus 2 minus beta. Two power beta plus channel capacity. This is your channel capacity. Now see that we have a beta value. So beta is what we had seen. Beta is already given in terms of the given probabilities 1 minus p. Okay, so we are going to simplify this log to the base 2 2 power beta plus 2. Okay, so on simplification we get beta is equal to beta to log to the base 2 of 2. Since log to the base 2 of 2 is equal to 1, we can write it as log to the base 2 of 2 power beta. So just simplifying inside. So we get the mutual information as maximum mutual information as I of x is to y is equal to log to the base 2 2 power beta plus 2 minus log to the base 2 2 power beta. So instead of this beta, we are substituting log to the base 2 2 power beta as here. And again, you can simplify further by using the logarithmic mathematical tool. Log to the base 2 2 power beta plus 2 divided by 2 power beta. So where beta is p log to the base 2 1 by p plus 1 minus p log to the base 2 1 by 1 minus p. So this represents this equation, whereas this equation I of x is to y is equal to log to the base 2 2 power beta plus 2 divided by 2 power beta with beta coordinates is the capacity of this ternary channel. Ternary channel. So any doubts in this problem solving, you can type in the chat box. I'll give you 2 or 3 minutes for viewing this solution such that we'll start another topic. So it took at least half an hour for me. I think so. More than half an hour, right? More than half an hour for solving or for explaining this problem. By using this procedure, it will be easier for you, step by step. For ternary channel. Again. So now we have found source center of h of x, mutual information I of x is to y, and also the capacity of the channel. Let me check for any questions in the chat box. Okay. So since there are no questions, I am making it as note that no questions for this problem, no queries. So these are the references. Abramson Information and Coding, Mansoorpur Introduction to Information Theory, RB Ash Information Theory, Error Control Coding by Shulin and Costello, Information and Coding Theory by G.A. Jones and J. Mary Jones. Okay. So with this, we complete unit number 2. With these problems, we complete unit number 2. Okay. And I think yesterday you'd have received the circular regarding first internal assessment test, and the portion for information theory and coding is unit 1 and 2. Unit 1 and Unit 2 will be your portion for information theory and coding. Keep in mind, or I'll just type in the chat box. First internal test will be scheduled, I think it is on Wednesday. Let me check the date also. It is 23, I think so. 23rd for all professional active. First internal examination on 23 9 2020 afternoon. Portion or syllabus, we can call it as syllabus is unit 1 and 2. Subject information theory code. Yeah, you can check the chat box for the syllabus to be conducted for information theory and coding unit 1 and 2, since you had completed. Okay. The mode of examination, or how the question paper will be shared, I'll be discussing that in another class. Still, I haven't finalized how to conduct first internal examination for information theory and coding. I will let you know, since 2 weeks are there. 1 week before, or in next week. Next week, I'll let you know how we are going to, or how you will be scripting or writing or uploading your first internal examination for information theory and coding subject alone. Okay, that I'll tell you in next class. So next week, not next class, next week. Okay, so we will move on to the next topic. And for your kind information, that these 2 units material will be shared today. I think already I had shared first unit's material in Google Classroom, and unit 2's material will be shared today. And let me post now itself. I post now itself. or else I'll forget. So let me post the material. Just give me 2 or 3 minutes such that I'll post the entire. Let me upload the files in Google Classroom. Kindly await. Oh, I haven't converted it to PDF.
பாருங்க ஆப்ஷனே இல்லை போற ஒண்ணு எழுத கொடுத்துட்டீங்க அவன் ஏதோ பெண்டிங் பேசுறேன்னு சொல்றானா அது வந்து
Another 2 or 3 minutes, we'll start the next session. So kindly await. I'll share you the material for unit first assess. I hope you would have received the material for unit 2 in your Google Classroom. So kindly check in your Google Classroom. The material is being posted for unit 2 now. Just now I had posted. So then we'll start unit number 3. Unit 3 is channels and optimal codes. In this channels and optimum codes, what are the things that we are going to see is that we are going to see about the decision rules on determining the channel, how to improve its reliability. Always the channel is unreliable. So with an example, we'll see how do we improve its reliability. Next is that Hamming distance. So with a problem of Hamming distance, we'll solve that in the fourth unit. Just the definition of Hamming distance we'll see. The statement and proof of Shannon's theorem, the converse of Shannon's theorem, followed by optimality of binary Huffman codes, then R array Huffman codes, and the extension to the sources. So I think most of you all are familiar with Shannon's theorem. So that theorem statement and proof you are going to see. And in addition to that, you would have here the Huffman coding also. So the Huffman coding, which you had done in unit 1, I think so, for solving a specific problem using Shannon-Fanon coding and using Huffman coding. Parallelly, we had done both together. So that example, I'll be recording how to solve that and how to solve using the RRI. How to use the Huffman coding in going to see a specific case. And after the specific case of ternary in Huffman codes, we'll be seeing it for an extension of sources. So these are the things which are being present in unit number 3 that we are going to see in unit number 3, all these things. In most of the unit 3, we'll be seeing basically about the Shannon's theorem, the Huffman coding that we had seen already. So I'll just give you a glimpse of that. We have only 2 or 3 problems to be solved in this unit 3. Only 2 or 3 problems. So mostly this unit 3 will be dealing only with theoretical concept oriented. Okay. So for that we need to recall that the Shannon's theorem, which is the most important in information theory, which is a relation between the capacity and the upper bound of data rates. Relation to the capacity and the upper bound of data rates. So it states that the capacity of the channel with an upper bound of data rate should have maximum information to be transmitted through it. So this we had seen in the earlier chapter. And the next is that a proof of the Shannon's theorem is quite difficult. So for simplicity, we have taken the proof of case for binary symmetric channel. BSC is a binary symmetric channel. Okay, so we are done for that. It is very tedious for non-binary, which we call it as M or R. M is equal to above 2. It's very difficult to prove in, or it is very difficult to understand using Shannon's theorem. So for that, we'll be using a Huffman's. So we'll see that also Huffman. So here the representation is being changed. Do not confuse with the unit 1's representation, unit 2's representation. All are inputs. Okay. Inputs A and outputs B. In previous, we had seen input X, output Y. So that is the difference. In information channel, we'll be having input and output only. So the representation of that will differ, that's all. So the receiver has output symbol B is equal to Bj belonging to B. As we had seen in problems that output represents I is equal to 1 to M in the same way, and X having J to N, the same way we are representing in terms of Bj for output and in terms of input EI. So this is difference, that's all. Okay, so how do we take a decision on this? So decision such that it will encode or a proper information rate can be determined is by applying this. Okay, so this is. So that decision is taken by decision rule, that is del. Del, where B is obtained from A. So this is a decision rule. So the decision rule is that a function del or decision rule depends upon B is always obtained from A, because B is your output and A is your input. Always we'll get the output only from A. So therefore the Bj emerges from tau and the receiver applies del to Bj AI determines AI is equal to del of B of J, which decides possibly. So then we can write the equation I is equal to J star. Next decision rule is that for the same binary symmetric channel having A is equal to B with symmetric, so we can write in terms of Z2, and we are making that this is a trustworthy channel. So what is this trustworthy channel is that if, for example, a channel which transmits an information without any errors, you can call it as trustworthy channel. For example, if you send a sequence of 4 ones in a channel, the output is also 4 ones, so then it is a trustworthy channel. And if the receiver receives the same, and this becomes a non-trustworthy when we send 4 ones in sequence, and if there is any errors or if there is any bits being absorbed by the channel. For example, in the 4 ones in sequence I send it, and the second bit or the first bit is getting missed. Instead of 1, it is being transmitted as 0. In that case, that is a non-trustworthy channel. So this is how to decide. Okay. So the decision of occurrence of 0 is 0, and decision of occurrence of 1 is always 1. So we'll see that with an example, don't worry. Okay. And if the receiver has AJ that was sent earlier, then the probability of decision will be this one only. Probability of occurrence of R, A is equal to AJ, or B is equal to BJ, which is Q into J into J.
100 கிலோ 100 ரூபாய். இதே தூரத்துல தள்ளி வண்டியில 3 கிலோ 100 ரூபாய். அவசரம்.
So then next is the probability of occurrence of Qj over the average function. So for average function, we are writing it as PRC. So the joint probability PR can be obtained as for error. So PRC is your average probability. PRE is the average probability in incorrect decoding. So means that if there is an error, we get 1 minus PRC. So it is 1 minus this PRC, substitute it as it is. Substitute this as it is. So we'll get, since we have found PRC, summation J is equal to Qj cross. We can substitute that here easily. So the decision rule plays a vital role for an observer such that the probability of occurrence of error is being minimized. So take the decision rule, which minimizes the error probability. And this rule is always made as an ideal observer rule for each j and for each I that we choose for maximum backward probability. For maximum backward probability, we need to choose this. So this is always equivalent to the maximum joint probability. So we'll see that with an example. So the example is this. The decision of B lies over in the case of equality. In a binary symmetric channel, we have the binary symmetric channel as this: P 0 0 P bar, and here capital P bar P. So from this we can find easily what is this Rij is. So simply multiply P into P P bar P bar and P bar P. So this is a general notation of that. So from this we can take the decision of probability of 0. We can take the decision of probability of 0 and the decision of 1 also. So the probability of 0 will be 0. The decision of 0 will be 0 if P small p capital P greater than P bar. If this is greater than this, we get 0. And if this is not greater than this, we get 1. So this is for decision of 0. And the decision of 1, if it is 1, P bar P greater than P bar, and it is 0 if P P bar P less than P, P bar. And this is equally applicable for case of equality. Decision rule. Next is your reliability. That to improve reliability. So in the binary symmetric channel, we cannot rely on information if a decision goes wrong. If the decision of 0 is correct, we may get the probability of occurrences of 0 or 1. And if the decision goes in 1 of 0 or 1, it may go wrong if the decision taken in the occurrence of probability is wrong. So for that, we need to look out about the channel characteristics. So if the channel characteristics are reliable, the decision rule will work correctly. If the channel characteristics are unreliable, or if the channel is an unreliable channel, so then the decision whatever we take will go in vain. So for that, we need to choose an appropriate reliable channel, assuming that the channel gives lesser probability of occurrence of error and more efficiency. So that we'll see with an example. I consider a binary symmetric channel. I consider a binary symmetric channel with Q and P bar, and I can write the matrix as M is equal to PQ QP, where Q can be defined as P bar, where P bar is 1 minus P. And most of you would be wondering, sir, in the problems we had solved P, probability of occurrence of error for 0, and 1 minus P for the probability of occurrence of error as 1. So here is the answer for that. 1 minus P is written as P bar. That I am writing in terms of Q. Only the notation is changed. Scripting the notation is changed. Why? Because this is your this material is taken from your referred textbook, G.A. Jonas and Mary Jonas textbook. From that, this material is being referred, or it is being cited from there. So there, the notation is like this: P, P, and instead of 1 minus P, it is Q or P bar. So P bar p bar q or 1 minus p. So the remaining coordinates remains the same. Always your rows are your inputs, columns are your outputs. So now we consider that the inputs are equiprobable in nature and the occurrence of the error is 1 by 2. It's a binary symmetric channel, 1 by 2. And the mutual information can be determined having a maximum channel capacity also. So the probability of error will be PRE that we are going to determine. We consider that the error probability is unexpectedly high, higher expectation. So I take an input sequence. Let us try with an input sequence. A is equal to 0 or 1. With A is equal to 0 or 1 and I send it in succession for 3 times. So I send a message in succession with 3 times of either 0 in succession of 3 times or 1 in succession of 3 times. So then our code will become in sequence as if I send 0, 3 zeros. If I send 1, 3 ones as it is. For this input C, we need to determine the code words. So wait for equivalent codes. So that can be determined by W. Equiprobable words for 000 and 111. So during the transmission of this, what are the maximum possibles that we have to see? Okay, how do we see that sense? 3 times in succession, we get 3 bits, either 3 zeros to 3 ones. So when I send, the possibility of occurring will be right from this 000, 001, 011, 100, 011, 101, 110, 4 ones. Each having of length 3. Why do we get length 3 is that we are sending in succession 3 times. So always our word length will be 3. Now each symbol will have this probability. So the probability of occurrence in the sequences could vary from this binary words 000 to 4 ones. So I can write, or we can write the decision based upon this rows and columns as this. If I want everything to be as zeros, I can write 00, 001, 010, 100. Okay, and similarly for 3 ones. So this is a decision rule 011, 101, 110, 111. So this is a decision rule for that. Okay, so we can decode this with a simple procedure. We can decode this with a simple decoding function by making decode symbol. For all this, we can decode it as 0. For all this, we can decode it as 1. So 0 and 1. So this is how do we improve it. And we decode it accordingly. So what is this is called as that we can take the maximum occurrence of words of symbols, either zeros or ones. We can take that, and which is the most frequent. So you can see that in this the most frequent is 0. So you can see that here 3 zeros, 2 zeros, 2 zeros, 2 zeros. So most frequent in this series is 0. So you can decode it as 0. And this the most frequent or the guaranteed symbol we can call it as is always 1. So 2 ones, 2 ones, 2 ones, 2 ones. So we can decode it as 1. So this is how to improve the reliability. You can see that with an example. The whole process of encoding, transmitting and decoding in a small diagram. I want to transmit either the form of 0 or 1. So for 3 succession informations, 000 I am writing, 111 I am writing. So they will be equally decoded on the channel. So this is your encoding part. This is your encoding part. Okay, this is your encoding part. This is your transmitting part. And this is your decoding part. This is your decoding part. So in this, the appropriate selection will be done. So these are the maximum possibilities. Since it is 3 successions, so 2 power 3, 2 power 3, we get 8 sequences, 101, 110, 111. So my desire is to transmit 0 or 1. Okay. So if I select 0, it will select this 00. And if I want 1, so 111. So this will be decoded accordingly. So this is your decoding part. This is what the description is given. This is your reliability of the channel. This is how to find the probability of error, PRE. Okay. For example, we are taking for n less than 11 and the q value to be as some values like this. So we can determine it for till up to 11. So the probability of error for n is equal to 1 will be this, n is equal to 3, n is equal to 5, n is equal to 7, n is equal to 9, n is equal to 11. I substitute it in this equation. So the improvement in reliability was efficiently done by Shannon's theorem. With the Shannon's theorem. So that we'll see in next class. Shannon's theorem. Okay. Okay, I think it's 11:25. But let me take that class. So we'll see the remaining topics next class. I was a bit slow today. Sorry for that. Let me take the attendance. Just a moment. Do not leave the meeting. I'll take attendance. Okay. Kindly turn on your mic and give attendance. Sai Vamsi. Harshavardhan.
Time, sir.
Okay. You can leave Harshavardhan. Sri
Our
Vishnu.
call came, sir.
Sri Vishnu. Venkat Sivasai,
Present, sir.
Purna Venkat.
Yes, sir. Present, sir.
You can leave. Sai Shri. Yeah, your name? Your name, please. Who gave attendance just now?
Sir.
Sai Shrikar.
Present, sir.
Sai Shrikar.
Present, sir.
Yeah, you can leave. Sai Shrikar.
Thank you,
Yes,
sir.
your name, please. Pavan Chandra.
Present, sir.
You can leave. Naresh Reddy.
Present, sir.
Okay, you can leave. Tanuja. You can leave. Kalyan Reddy. Pavan Kalyan. Lakshmanan. Okay, you can leave Lakshman. Tanuja can leave. Pranit.
Present, sir.
You can leave. Harshita.
Present, sir.
You can leave. Sudhit Chandana.
Present, sir.
You can leave. Manashwini.
Present, sir.
You can leave. Kishore.
Yes, sir. Present, sir.
You can leave Kishore. Vamsi. K Vamsi. K Vamsi. Reddy Kumar. Srikala.
Present, sir.
You can leave. Sai Srija.
Present, sir.
Sai Srija. Yeah, you can leave. So is there anybody else left out?
Sir,
Ah, you can leave.
sir,
Anybody is left out?
sir, my attendance is pending,
Yes,
sir.
your name?
Vamshi. Vamshi, sir, Sai Vamshi, C009.
Name.
Vamshi, sir, Sai Vamshi.
Okay. Okay, Ra.
Okay.
Okay, C009. Attendance is marked.
Yes, sir. Yes, sir. Call game,
Sir, can you leave, sir?
attendance is taking.
16.
Okay.
Hello, sir.
Okay, no problem.
Okay, sir. Thank you, sir.
Ah, yes.
16, sir.
Okay. Your name?
Acha, sir.
Ah, Harshavardhan is marked.
Okay.
Harshavardhan, right?
You didn't say can you leave the class, sir.
Harshavardhan
That's
is
why I
marked.
asked.
Okay, no problem. Harsha can leave. Okay. Thank you.